Hi everyone, this is Kaveri. Today I am going to explain about the second chapter that is operating system structures. An operating system provides the environment within which our programs are executed. Internally, operating systems vary greatly in their makeup since they are organized along many different lines. Now, an operating system is a crucial piece of a software that manages computers' hardware and provides an interface for users and the applications to interact with the system. Here, the design of a new operating system is a major task, and it is important that the goals of the system be well defined before the operating system design begins. Now in this chapter we explore all three aspects of operating system, showing the viewpoints of users, programmers and operating system designers. We consider what services an operating system provides, how they are provided, and what what the various methodologies are for designing such a systems. And now operating system services. Operating system provides an environment for the execution of a programs. It provides a certain services to perform to program and the users of those programs. And operating system services are provided for the convenience of the programmer to make the programming task easier. These services from the core of an operating system responsibilities and play a crucial role in facilitating user interactions and application execution. One set operating system services provide a function that are helpful to the user. First one, user interface. User interface almost all operating systems have a user interface. This interface can take several forms. Means user interface has two approaches. First one is command line interface and second is graphical user interface. User interface is an operating system in a means through which a user interact with and a control of a computer system. It acts as an intermediate between users and the underlying system. Another is a batch interface in which a commands and directives to control those commands are entered into files and those files are executed. Most commonly, a graphical user interface. The interface is a window system with a pointing devices. Choose from menus and make selections and keyboards enter text. In further topics, we'll study in detail about this command line interface and a graphical. Now, program execution. The system must be able to load a program. It should be able to load the program into memory and run the program. The program must able to end its execution either normally or abnormally. It should be end the program execution either normally or it in in indicating error. The program execution process begins with leading the program into memory from storage. For example, hard drive and solid state drive. The operating system is responsible for managing these loading processes and allocating the memory for the program. I/O operations. A running program may require I/O which may involve a file or an I/O device. For a specific device, special functions may be desired such as recording to CD or DVD drive or blanking CRT screen. These I/O operations are essential in computing as they allow data to be transferred between computer central process unit, that is CPU, and external devices. These I/O devices include peripherals such as keyboard, mouse, monitors, printers, storage drives, USB, etc. Each device has its own control that facilitate a communication between device and the CPU. These instruction enables the CPU to interact with I/O devices, send commands, and transfer the data. Users usually cannot control I/O devices directly. Therefore, the operating system must provide a means to do I/O devices, means input-output devices. Next, file system manipulation. File system is of particular interest. Obviously, a program need to read or write of files or directories. They also need to create and delete them by name, search for given file, and list of information. Uh, File system manipulation involves various operations and tasks related to managing files and directories within an operating system. File creation is a process of generating a new file on a file system. These operations allow user to application to create and read, write, delete, move, or organize a files and folder. Finally, some programs include permissions management to allow or deny access to files or directories based on a file ownership. And coming to next, this is communication. There are many circumstances in which a process need to exchange information and other processes with another processes. Such communication may occur between processes and that are executing on the same computer or between processes that are executing on the different computer systems tied together by a computer network. Communication can be implemented by shared memory or through a message passing, in which a packets of the informations are moved between process by the operating system. Uh, there are many circumstances in this process need to exchange the information with another process. It refers to the exchange of information, data or signals between different components, processes or devices with the system. Communication may be implemented via shared memory or through a message passing. The communication may be implemented by shared memory or through message passing, in which a packets of information moved between the processes by the operating system. Now, error detection. An operating system needs to be constantly aware of possible errors. Error may occur in CPU and memory hardware as a memory error or such as a memory error or a power failure. In I/O devices such as a parity error on a tape, a connection failure on a network, or lack paper in the printer and in the user program. Uh, it should be aware of some possible errors. The errors may occur in a CPU and memory hardware. It involves the implementing mechanism to identify and handle the errors that may occur within the various components and data structures of the operating system. For each type of error, operating system should take the appropriate action to ensure the correct and consistent computing. And here, the operating system should take appropriate action to ensure the correct and consistent computing. Debugging facilities can greatly enhance the users and programmers' ability to use the system efficiently. Debugging facility can enhance the users and programmers' ability to use the system efficiency. Systems with a multiple user can gain efficiency by sharing the computer's research among the users. Then comes resource allocation. Resource allocation, when there is a multiple users or a multiple jobs running at a same time, resources must be allocated to each of them. Many different types of resources are managed by the operating system. Some may have a special allocation code, whereas others may have a much more allocation general requests and release code. It refers to the process of managing and distributing system resources to different user applications and process running on the operating system. Many different types of resources are managed by the operating system. Some of them have a special allocation code and some others may have such a general request, have much general request and release code. For instance, in determining how best the use of CPU, operating system have CPU scheduling routine that take into account the speed of the CPU. It has a CPU scheduling routine that take into accurate that the speed of the CPU is, the jobs that must be executed, the number of registers available, and other factors. There may also be routine to allocate the printers, models, USB storage, or another peripheral devices. It can be allocated many printers, modems, or USB storage devices, and other peripheral devices also. And then accounting. We want to keep a track which user use how much and what kind of computer resources. We should have a track on on which a user is using and how much and what kind of a computer resources he is using. It refers accounting. Accounting is it refers to a process of tracking and recording a resources usage and activities or individual users or process on a computer system. Usage statistic may be a valuable tool for researchers who wish to recording the system to improve computing services. It involves collecting the information about how users interact with the operating system, the resources they consume, and the tasks they perform. The data gathered through accounting can be valuable for various purposes such as billing, performance analysis, resource optimization, security, auditing, etc. Then comes last, that is protection and security. The owner of the information stored in the multi-user or a networked computer system may want to control use of the information. Protection security comes it's like a password pin using this etc. The owner or a usage of that particular system, the stored information in the multi-user or networked computer system, that should be control the use of that information. When a several then when several separated processes execute concurrently, if the several separated processes executed concurrently, it should not be possible for the one processor to interact with others and also it is not possible to interact with the operating system itself. It should have user authentication, means implementing a reverse user authentication mechanism such as a password, PIN, biometrics, or multi-factor authentication to verify the to verify the identity of the user before the uh, grantee access to the system. And also it involves the encrypted communication, means using the encryption for the communication between the user interface and the OS to protect the sensitive data from the interactions and tampering. Storing the information like password using a strong cryptographic hashing algorithm with a salt to protect them. It including modem and network adapters from invalid access attempts and recording all such a connections for detecting of a break lines. If the system is to be protected and secured, precaution must be instituted throughout it. By incorporating these protections and security measures into the user operating system interface, user can interact with the system confidently, knowing that their data and resources are well protected against the potential threats and unauthorized access. Now, next move to users operating system interface. There are two fundamental approaches. As we started briefly about these topics in last topic, user operating system interface in earlier. Now we'll understand these topics some completely or detailedly. There are two fundamental approaches. First one is command interpreter and second one is graphical user interface. One technique is the first one technique is to provide the command line interface that allows user to directly enter the commands, means that are be performed by the operating system. And the second approach allows the user to interface with the operating system by graphic GUI, that is graphic user interface. Now command interpreter. Some operating systems include the command interpreter in the kernel. Some of the OS involve the command interpreter in kernel and some other like Windows, XP and Unix treat the command interpreter as a special program that uh, that is running when a job is initiated. A system with a multiple command interpreter to choose up from the interpreter is known as a shell. One system with multiple command interpreters to choose from. The interpreters are known as shell. For example, Unix and Linux. There are several different shells user may choose from, including Bourne shell, C shell, Bourne again shell, and Corn shell, etc. User choose a shell according to their personal preference. Here, the most shell provides a similar functionality. It can provide a similar function with only small differences in it. Most users choose the shell based upon or according to their personal preference. The main function of the command interpreter is to get and execute the user and specified command. In an approach, there are two general ways in which these commands can be implemented. In one approach, the command interpreter itself contains the code to execute a command. For example, a command to delete a file may cause the command interpreter to jump to a section of a code that sets the parameters and makes the appropriate system calls. In this case, the number of commands that can be given determines the size of the command interpreter, and each individual command requests its own implementing code, and it merely uses the command to identify a file to be loaded into memory and executed. Thus, the Unix command is delete a file. The Unix command to delete the file. Second approach is used by Unix, that among the other operating system implements the most command through system programs. In this case, the command interpreter does not understand the command in any way. It merely uses a command to identify the file to be loaded and memory and executed. Thus, Unix command deletes the file. Here. In this way, programmers and users can add a new commands to the system easily by creating a new files with a proper names. The command interpreter program, which can be small, the interpreter means the command interpreter program that can be small, and it does not have to be changed for a new command to be added. It cannot means it does not have to be changed for adding the new command to it. Next comes graphical user interface. GUI means graphical user interface is a type of a user interface that allows user to interact with a computer system or software applications using a graphical elements such as icons, buttons, windows, and menus. The second strategy for interfacing with the operating system is through a user-friendly graphical user interface, or GUL, rather than having user directly enter the commands via command line interface. Graphical user interface it is appear due in a part of a research taking place in the early 1970s at Xerox PARC research facility. Unix systems have been dominated by command line interface, although there are various GUI interface available, including a common desktop environment, that is CDE, and X Windows system that are common on commercial variants of Unix. Traditionally Unix systems have been dominated by command line interface, although there is various GUI interface available, including the common desktop environment, as I already said this, and X Windows system that are commonly on commercial version of Unix, such as Solaris of IBM's systems. The choice of whether to use the choice of whether to use a GUI interface mostly, or we should use a command line, or we should use a GUI mostly one of personal preferences. As the rule nowadays, as generally nowadays we are all the Unix users use command line interface, as they give or provide good or powerful interfaces or powerful shell interfaces, and alternatively many Windows users often use a Windows GUI environment, and mostly they do not use the MS-DOS, that is Microsoft Disk Operating System shell in interface. The user interface can vary from system to system. The user's interface interaction with the interaction vary from systems to systems or user to user. It typically substantially removed from the actual system structures. The design of useful and friendly user interface, therefore not direct function of the operating system. it is user-friendly interface system. So therefore, not a direct function of the operating system is there. It can we don't differentiate now. We don't differentiate the or distinguish the user programs and the system programs in this.
System calls. System calls provide an interface to the services made available by an operating system. These calls are generally available as routines written in C and C++, although certain low-level tasks, for example, tasks where hardware must be accessed directly, may need to be written using assembly language instructions. Before we discuss how an operating system makes system calls available, let's first use an example to illustrate how system calls are used, writing a simple program to read data from one file and copy them to another file. The first input that the program will need is the names of the two files, the input file and the output file. These names can be specified in many ways, depending on the operating system design. One approach is for the program to ask the user for the names of the two files. In an interactive system, this approach will require a sequence of system calls, first to write a prompting message on the screen and then to read from the keyboard the characters that define the two files. On mouse-based and icon-based systems, a menu of file names is usually displayed in a window. The user can then use the mouse to select the source name, and a window can be opened for the destination name to be specified. This sequence requires many I/O system calls. Once the two file names are obtained, the program must open the input file and create the output file. Each of these operations requires another system call. There are also possible error conditions for each operation. When the program tries to open the input file, it may find that there is no file of that name or that the file is protected against access. In these cases, the program should print a message on the console, another sequence of system calls, and then terminate abnormally another system call. If the input file exists, then we must create a new output file. We may find that there is already an output file with the same name. This situation may cause the program to abort a system call, or we may delete the existing file, another system call, and create a new one, another system call. Another option, in an interactive system, is to ask the user via a sequence of system calls to output the prompting message and to read the response from the terminal, whether to replace the existing file or to abort the program. Now that both files are set up, we enter a loop that reads from the input file a system call and writes to the output file another system call. Each read and write must return status information regarding various possible error conditions. On input, the program may find that the end of the file has been reached or that there was a hardware failure in the read, such as a parity error. The write operation may encounter various errors, depending on the output device, no more disk space, printer out of paper, and so on. Finally, after the entire file is copied, the program may close both files. Another system call, write a message to the console or window, more system calls, and finally terminate normally the final system call. As we can see, even simple programs may make heavy use of the operating system. Frequently, systems execute thousands of system calls per second. This system call sequence is shown in Figure 2.1. Most programmers never see this level of detail, however. Typically, application developers design programs according to an application programming interface API. The API specifies a set of functions that are available to an application programmer, including the parameters that are passed to each source file. Destination file is an example of a standard API. Consider the read file queue function in the Win32 API, a function for reading from a file. The API for this function appears a description of the parameters passed to read file O is as follows. Handle file, the file to be read. LPVOID buffer, a buffer where the data will be read into and written from. DWord bytes to read, the number of bytes to be read into the buffer. LPD word bytes read, the number of bytes read during the last read. LP overlapped OVL, I indicates IF overlapped IOIS being used, function and the return values the programmer can expect. Three of the most common APIs available to application programmers are the Win32 API for Windows systems, the POSIX API for POSIX-based systems, which includes virtually all versions of Unix, Linux, and Mac OS X, and the Java API for designing programs that run on the Java virtual machine. Note that the system call names used throughout this text are generic. Examples: each operating system has its own name for each system call. Behind the scenes, the functions that make up an API typically invoke the actual system calls on behalf of the application programmer. For example, the Win32 function create process, which unsurprisingly is used to create a new process, actually calls the ntcreate process system call in the Windows kernel. Why would an application programmer prefer programming according to an API rather than invoking actual system calls? There are several reasons for doing so. One benefit of programming according to an API concerns program portability. An application programmer designing a program using an API can expect her program to compile and run on any system that supports the same API, although in reality, architectural differences often make this more difficult than it may appear. Furthermore, actual system calls can often be more detailed and difficult to work with than the API available to an application programmer. Regardless, there often exists a strong correlation between invoking a function in the API and its associated system call within the kernel. In fact, many of the POSIX and Win32 APIs are similar to the native system calls provided by the Unix, Linux, and Windows operating systems. The runtime support system, a set of functions built into libraries included with a compiler for most programming languages, provides a system call interface that serves as the link to system calls made available by the operating system. The system call interface intercepts function calls in the API and invokes the necessary system call within the operating system. Typically, a number is associated with each system call, and the system call interface maintains a table indexed according to these numbers. The system call interface then invokes the intended system call in the operating system kernel and returns the status of the system call and any return values. The caller needs to know nothing about how the system call is implemented or what it does during execution. Rather, it just needs to obey the API and understand what the operating system will do as a result of the execution of that system call. Thus, most of the details of the operating system interface are hidden from the programmer by the API and are managed by the runtime support library. The relationship between an API, the system call interface, and the operating system is shown in Figure 2.3, which illustrates how the operating system handles a user application invoking the open system call. System calls occur in different ways, depending on the computer in use. Often, more information is required than simply the identity of the desired system call. The exact type and amount of information vary according to the particular operating system in call. For example, to get input, we may need to specify the file or device to use as the source, as well as the address and length of the memory buffer into which the input should be read. Of course, the device or file and length may be implicit in the call. Three general methods are used to pass parameters to the operating system. The simplest approach is to pass the parameters in registers. In some cases, however, there may be more parameters than registers. In these cases, the parameters are generally stored in a block, or table, in memory, and the address of the block is passed as a parameter in a register. Figure 2.4. This is the approach taken by Linux and Solaris. Parameters also can be placed, or pushed, onto the stack by the program and popped off the stack by the operating system. Some operating systems prefer the block or stack method, because those approaches do not limit the number or length of parameters being passed. 2.4 Types of system calls. System calls can be grouped roughly into 5 major categories: process control, file manipulation, device manipulation, information maintenance, and communications. In sections 2.4.1 through 2.4.5, we discuss briefly the types of system calls that may be provided by an operating system. Most of these system calls support, or are supported by, concepts and functions that are discussed in later chapters. Figure 2.5 summarizes the types of system calls normally provided by an operating system. 2.4.1 Process control. A running program needs to be able to halt its execution either normally and or abnormally abort if a system call is made to terminate the currently running program abnormally, or if the program runs into a problem and Causes an error trap. A dump of memory is sometimes taken in an error. Message generated. The dump is written to disk and may be examined by a debugger, a system program designed to aid the programmer in finding and correcting bugs, to determine the cause of the problem. Under either normal or abnormal circumstances, the operating system must transfer control to the process control. O end, abort, O load, execute, O create process, terminate process. O get process attributes, set process attributes. O wait for time, O wait event, signal event. O allocate and free memory. File management, degree create file, delete file. O open, close, degree read, write, reposition. O get file attributes, set file attributes. Device management, O request device, release device. Degree read, write, reposition. O get device attributes, set device attributes. Degree logically attach or detach devices. Information maintenance. O get time or date, set time or date. O get system data, set system data. O get process, file, or device attributes. O set process, file, or device attributes. Communications. 0. Create, delete communication connection. Degree send, receive messages. O transfer status information. O attach or detach remote devices. Figure 2.5 Types of system calls. Invoking command interpreter. The command interpreter then reads the next command. In an interactive system, the command interpreter simply continues with the next command. It is assumed that the user will issue an appropriate command to respond to any error. In a GUI system, a pop-up window might alert the user to the error and ask for guidance. In a batch system, the command interpreter usually turns.
Now, let us learn about system programs. Collection of programs that provide a convenient environment for program development and execution are called system programs or system utilities. Some of them are simply user interfaces to system calls, others are considerably more complex. They can be divided into different categories. First, file management. This helps programs to create, delete, copy, rename, print, or generally manipulate files and directories. Next, status information. Utilities to check on date, time, number of users, processors running, data logging, etc. System registers are used to store and recall configuration information for particular applications. Third, file modification. It helps in modification of the file. Example, text editors and other tools which can change the file contents. Programming language support. Example, compilers, linkers, debuggers, profilers, assemblers, library archive management, interpreters for common languages, and support for Make. Program loading and execution. Once a program is assembled or compiled, it must be loaded into memory to be executed. The system may provide absolute loaders, reallocatable loaders, linkage editors, and overlay loaders. Debugging system for either higher level languages or machine languages are needed as well. Communication. These programs provide the mechanism for creating virtual connections among processors, users, and computer systems. They allow users to send messages to one another's screen, to browse web pages, and to send electronic mail messages, to log on remotely, or transfer files from one machine to another machine. Next, we will be looking after operating system design and implementation. First, let us look about design goals. The first problem in designing a system is to define goals and specifications. At the highest level, the design of system will be affected by the choice of hardware and type of system. Batch, time shared, single user, multi-user, distributed, real-time, or general purpose. Beyond this highest design level, the requirements may be much harder to specify. The requirements can, however, be divided into two basic groups: user goals, system goals. User goals or user requirements are the features that user care about and understand, like system should be convenient to use, easy to learn, reliable, and safe and fast. System requirements or system goals are written for the developers, that is, people who design the operating system. Their requirements are like easy to design, implement, and maintain, flexible, reliable, error free, and efficient. Next, let us look after mechanism and policies. Policies determine what is to be done. Mechanism determine how it is to be implemented. Example, in timer counter and decrementing counter is the mechanism, and deciding how long the time has to be set is the policies. Policies change over time. In the worst case, each change in policy would require a change in underlying mechanism. If properly separated and implemented, policy changes can be easily adjusted without rewriting the code, just by adjusting parameters or possibly loading new data or configuration files. Next, let us look after implementation. Traditionally, operating systems were written in assembly language. In recent years, operating systems are written in C or C++. Critical sections of code are still written in assembly language. The first operating system that was not written in assembly language, it was the master control program. The advantages of using higher level language for implementing operating system are: the code can be written faster, more compact, easy to port or to other systems, and easier to understand and debug. The only disadvantage of implementing an operating system in higher language are reduced speed and increased storage requirements.
I'm going to talk about simple structure of operating system. Example of simple structure is MSDOS layout structure. MSDOS means Microsoft Disk Operating System, and as you can see in this 2.10 diagram, ROM BIOS device drivers are followed by MSDOS device drivers, resident system program, and then it is followed by application program. ROM BIOS a device driver means read only memory, a basic input output system device drivers, and through application program you can access to ROM drivers, and you can also access ROM drivers through resident system programs, and it is followed by MSDOS drivers device drivers. From that you can also access ROM BIOS device drivers, and like this many other operating systems are there, like Unix, Mac OS, and all the operating systems. Let us talk about Unix operating system. Unix is another system that initially was limited by hardware functionality. It consists of two separable parts, the kernel and system programs. The kernel is further separated into a series of interfaces and device drivers, which have been added and expanded over the years as Unix has evolved. We can view the traditional Unix operating system as being layered, as shown in 2.11 figure. Everything below the system call interface and above the physical hardware is the kernel. As you can see in this diagram, kernel is directly connected to the hardware. The kernel provides a file system, CPU scheduling, memory management, and other operating system functions through system calls, taking in sum that is enormous amount of functionality to be combined into one level. This monolithic structure was difficult to implement and maintain. As you can see, it is complicated, and let us see about layered approach. In this diagram you can see the user, and the kernel is directly connected to the hardware, and this shells and commands, compiler and interpreter, system libraries. Kernel does all the work to control all the functionalities. This was the Unix system structure, and this is the layered operating system, basic layered operating system you can see here. So let us see modules now. The current methodology for operating system design involves using object-oriented programming techniques to create a modular kernel. Here the kernel has a set of core of components and dynamically links in additional services either during a boot time or runtime. Such a strategy uses dynamically loadable modules and is common in for modern implementations of Unix such as Solaris, Linux, and macOS. Here you can see the example of Solaris loadable module. As you can see, core Solaris kernel serves everyone. Scheduling classes, file systems, loadable system calls, executable formats, streams, modules, miscellaneous, and device and bus drivers modules. These designs allows kernel to provide services to everyone. Like example, the Apple Macintosh Mac OS X operating system uses a hybrid structure. Mac OS, also known as Darwin structures the operating system using the layer technique, where one layer consists of Mac microkernel. The structure of Mac OS appears in 2.14, like you can see here. Here we have BSD. BSD means Berkeley Software Distribution, which is directly connected to the services which a kernel provides. So now let us talk about virtual machine. Let us know about virtual machine. What is virtual machine? A computer system created using software on one physical computer in order to emulate the functionality of another separate physical computer is known as virtual machine. So the fundamental idea behind virtual machine is to abstract the hardware of a single computer into several different execution environments, hereby creating the illusions that separates execution environment is running its own private computer. And there are several reasons to create a virtual machine, all of which are fundamentally related to being able to share the same hardware yet to run several different execution environments concurrently. A major difficulty with the virtual machine approach involves disk systems. Suppose that the physical machine has 3 disks. Here, 3 disk drives, but wants to support 7 virtual machines. Clearly, it cannot allocate a disk drive to each virtual machine because the virtual machine software itself will need a substantial disk space to provide virtual memory and spooling. And the solution for this is to provide virtual disk termed minidisc in IBM's VM operating system that are identical in all respect except sizes. As you can see the work of systems without virtual machine in this diagram, and this is the hardware which have virtual machines. And let us see the implementation of the virtual. As you can see, virtual machine is very convenient, but to develop and implement virtual machine is very difficult, and much work is required to provide an exact duplicate of underlying machine. The underlying machine has 2 modes, user mode and kernel mode. The virtual machine software can run in kernel mode since it is the operating system. The virtual machine itself can execute in only user mode, just as physical machine has 2 modes. However, so must the virtual machine. Consequently, we must have a virtual user mode and the virtual kernel mode, both of which run in a physical user. Those actions that cause a transfer from user mode to kernel mode on real machine must also cause a transfer from virtual user mode to virtual kernel mode on a virtual machine. Such transfers can be accomplished as follows. When a system call, for example, is made by a program running on a virtual machine in virtual user mode, it will cause a transfer to the virtual machine monitor in the real machine. When the virtual machine monitor gains control, it can change the register contents and program counter for virtual machines to stimulate the effects of the system call. It can then restart the virtual machine, nothing that it is now in a virtual car. So let us see the benefits of virtual machine. The virtual machine have several advantages in this environment. There is complete reproduction of the various system resources. Each virtual machine is completely isolated from all other virtual machine, so there are no protection problems. At the same time, however, there is no direct sharing of resources. Two approaches to provide sharing have been implemented. First, it is possible to share a mini disk and thus to share files. This scheme is modeled after a physical shared disk, but it is implemented by software. Second, it is possible to define a network of virtual machine, each of which can send information over a virtual communication networks. Again, the network is modeled after physical communication networks, but it is implemented in software. So let us talk about VM, virtual machineWare. Here is the example of virtual machine architecture of virtual machineWare. As you can see, a host operating system like Linux is directly connected to the applications which user gives, and all these controls the operation. And here is the host and CPU which controls memory to store and input devices. Thank you.
Operating system generation. It is possible to design, code, and implement an operating system specifically for one machine at one site. More commonly, however, operating systems are designed to run on any of a class of machines at variety of sites with a variety of peripheral configuration. The system must then be configured or generated for each specific computer site, a process sometimes known as system generation. The operating system is normally distributed on disk or CD-ROM. To generate a system, we use special program. The sysgen program reads from a given file or asks the operator of the system for information concerning the specific configuration of the hardware system, or perhaps the hardware directly to determine what components are there. The following kinds of information must be determined. What CPU is to be used, what options, extended instruction sets, floating point, arithmetic, and so on are installed. For multiple CPU systems, each CPU must be described. How many memory is available? Some systems will determine this value themselves by referring memory location after memory location until an illegal address fault is generated. The procedure defines the final legal address and hence the amount of available memory. What devices are available? What operating systems options are desired or what parameter values are to be used. These options or values might include how many buffers of which size should be used, what type of CPU scheduling algorithm is desired, what the maximum number of processes to be supported is, and soon. Once this information is determined, it can be used in several ways. At one extreme, a system administrator can use it to modify a copy of the source code of the operating system. The operating system then is completely compiled, data declaration, initialization, and constants, along with conditional compilation, procedure, and output object version of the operating system that is tailored to the system described. At a slightly less tailored level, the system description can cause the creation of tables and the selection of modules from a precompiled library. These modules are linked together to form the generated operating system. Selection allows the library to contain the device drivers for all supported I/O devices, but only those needed are linked into the operating system. Because the system is not recompiled, system generation is faster, but the resulting system may be overly general. At the other extreme, it is possible to construct a system that is completely table driven. All the code is always part of the system and selection occurs at execution time rather than at compile or link time. System generation involves simply creating the appropriate tables to describe the system. The major differences among these approaches are the size of generally of the generated system and the S of modification as the hardware configuration changes. Consider the cost of modifying the system to support a newly acquired graphics terminal or another device. Balanced against that cost, of course, is frequency or infrequency of such changes.
After an operating system is generated, it must be made available for use by the hardware. But how does the hardware know where the kernel is, how to load that kernel? The procedure of starting a computer by loading the kernel is known as booting the system. On most computer systems, a small piece of code known as bootstrap program or bootstrap loader locates the kernel, loads it into main memory, and starts its execution. Some computer systems, such as a PCs, uses two-step process in which a simple bootstrap loader fetches a more complex boot program from disk, which in turn loads the kernel. When a CPU receives a reset event, for instance, when it is powered up or rebooted, the instruction register is loaded with a predefined memory location and execution starts here. At that location is the initial bootstrap program. This program is in the form of read-only memory ROM because the RAM is in unknown state at system startup. ROM is convenient because it needs no initialization and cannot be infected by computer virus. Bootstrap program can perform a variety of tasks. Usually one task is to run diagnostics to determine the state of the machine. If the diagnostics pass, the program can continue with the booting steps. It can also initialize all aspects of the system, from CPU registers to device controllers and the contents of the main memory. Sooner or later, it starts the operating system. Some systems, such as cellular phones, PDAs, and game consoles, store the entire operating system in ROM. Storing the operating system in ROM is suitable for small operating systems, simple supporting hardware, and rugged operation. A problem with this approach is that changing the bootstrap code requires changing the ROM hardware chips. Some system resolves this problem by using erasable programmable read-only memory, which reads only except when explicitly given a command to become a writable. All forms of ROM are also known as firmware, since their characteristics fall somewhere between those of the hardware, those of software. A problem with firmware in general is that executing code there is slower than executing code in RAM. Some systems store the operating system in firmware and copy it to RAM for fast execution. A final issue with firmware is that it is relatively expensive, so usually only small amounts are available. For large operating systems, including most general purpose operating systems like Windows, Mac OS, and Unix, or for systems that change frequently, the bootstrap loader is stored in firmware and the operating system is on disk. In this case, the bootstrap runs diagnostics and has a bit of code that can read a single block at a fixed location from disk into memory and execute the code from the book block. The program stored in the book block may be sophisticated enough to load the entire operating system into memory and begin its execution. More typically, it is simple code and only knows the address on disk and length of the remainder of the bootstrap program. All of the disk bound bootstrap and the operating system itself can be easily changed by the writing new versions to disk. A disk that has boot partition is called boot disk or system disk. Now that the full bootstrap program has been loaded, it can traverse the file system to find the operating system kernel, load it into memory, and starts its execution. It is only at this point that system is said to be running. After an operating system is generated, it must be made available for use by the hardware. But how does the hardware know where the kernel is, how to load that kernel? The procedure of starting a computer by loading the kernel is known as booting the system. On most computer systems, a small piece of code known as bootstrap program or bootstrap loader locates the kernel, loads it into main memory, and starts its execution. Some computer systems, such as a PCs, uses two-step process in which a simple bootstrap loader fetches a more complex boot program from disk, which in turn loads the kernel. When a CPU receives a reset event, for instance, when it is powered up or rebooted, the instruction register is loaded with a predefined memory location and execution starts here. At that location is the initial bootstrap program. This program is in the form of read-only memory ROM because the RAM is in unknown state at system startup. ROM is convenient because it needs no initialization and cannot be infected by computer virus. Bootstrap program can perform a variety of tasks. Usually one task is to run diagnostics to determine the state of the machine. If the diagnostics pass, the program can continue with the booting steps. It can also initialize all aspects of the system, from CPU registers to device controllers and the contents of the main memory. Sooner or later, it starts the operating system. Some systems, such as cellular phones, PDAs, and game consoles, store the entire operating system in ROM. Storing the operating system in ROM is suitable for small operating systems, simple supporting hardware, and rugged operation. A problem with this approach is that changing the bootstrap code requires changing the ROM hardware chips. Some system resolves this problem by using erasable programmable read-only memory, which reads only except when explicitly given a command to become a writable. All forms of ROM are also known as firmware, since their characteristics fall somewhere between those of the hardware, those of software. A problem with firmware in general is that executing code there is slower than executing code in RAM. Some systems store the operating system in firmware and copy it to RAM for fast execution. A final issue with firmware is that it is relatively expensive, so usually only small amounts are available. For large operating systems, including most general purpose operating systems like Windows, Mac OS, and Unix, or for systems that change frequently, the bootstrap loader is stored in firmware and the operating system is on disk. In this case, the bootstrap runs diagnostics and has a bit of code that can read a single block at a fixed location from disk into memory and execute the code from the book block. The program stored in the book block may be sophisticated enough to load the entire operating system into memory and begin its execution. More typically, it is simple code and only knows the address on disk and length of the remainder of the bootstrap program. All of the disk bound bootstrap and the operating system itself can be easily changed by the writing new versions to disk. A disk that has boot partition is called boot disk or system disk. Now that the full bootstrap program has been loaded, it can traverse the file system to find the operating system kernel, load it into memory, and starts its execution. It is only at this point that system is said to be running.
Myself Praveen Basha. I want to explain Chapter 2 Summary Part 2.11. Operating System provide a number of services at the lower level. System calls allow a running program to make requests from the operating system directly. At a higher level, the command interpreter or shell provides a mechanism for a user to issue a request without writing a program. Command may come from files during batch mode's execution or directly from a terminal when in an interactive or time-shared mode. System programs are provided to satisfy many common user requests. The types of requests vary according to level. The system call level must manipulation higher level requests, satisfied by the command interpreter or I0 request. Program errors can be considered implicit requests for service. For a computer system to begin running, the CPU must initialize and start executing the bootstrap program in firmware. Throughout the entire operating system design cycle,